last day online, and the first speaker is
Romolo, sorry if I interrupt you, but on YouTube, at least on my computer, I see.
But I suspect there is.
Now we are online.
Okay, now yes.
Online. There is a delay. The first speaker is there is.
Romolo, sorry if I interrupt you, but on YouTube, at least on my.
Yes.
No,
Okay. Okay. So the first speaker is Donatella Cassettari, that will give us a talk about the Bose-Einstein condensate in holographically generated optical traps. So please.
Yep. So I should have checked before, but can you hear me okay?
Yes.
Excellent. Thank you. So, well, let me start by thanking the organizers for inviting me, and indeed for putting together such a good conference. I was able remotely. I was able to tune in into some sessions since Monday, wishing I was there in person. So thank you very much for this opportunity, and maybe I will be there in person next time. So. For those of you who don't know me, my name is Donatella Cassettari. I work at the University of St. Andrews. Oh, too fast. Just a moment. So the general area of my talk is atomtronics. So the idea is to make circuits for cold atoms, which are equivalent or analogous to what we have in electronics, so circuit for electrons. And there is one recent review article covering the whole of atomtronics, which you can find here, and also on the AVQ Quantum Science journal. So this is a very good reference, very up to date. Within atomtronics, what I'm interested in is ring potential, so ring traps for atoms. So let me give you just a few examples of all the things that one can do with ring potentials. This is not exhaustive, it's just some examples of recent work. For instance, here you see from the group of Malcolm Boshier, they realized the atomic equivalent of a quantum interference device. So they did experiment, and this is something that is very interesting from the fundamental point of view. It's the first step towards working with flux qubits, as suggested here by Luigi Amico and collaborators. And in addition to the fundamental interest of this, there is also an interest for quantum sensing. For instance, these atomic squids can be used for sensing rotations. Then other exciting experiments that have come out of the atomtronics research community. Wolf von Klitzen and Ellen Perrin, they achieved supersonic Bose-Einstein condensates, as shown here. In the group of Gretchen Campbell, they did an experiment where they're simulating an expanding universe using an expanding Bose-Einstein condensate. So these are just examples of recent work, and that one can do with ring traps. And of course, if you have a ring, why stop at one? Let's have more than one ring. For instance, there are theoretical proposals by Nick Prokakis and by Veronika Haufinger to couple rings. And this can be done on a planar geometry like this, so two rings kind of touching each other, or using stacks of rings like this. And one can investigate interesting phenomena like having a certain winding number on one ring, and how does that get transferred to the other ring. Of course, we can take a ring and we can change it slightly. So we can go from a ring here to a what looks more like a racetrack potential here, and this is the work of Mark Edwards and Charles Clark. So, but there are many more things that people are working on. So it's a very rich field. So now, what we do in St. Andrews, we work on atomtronic circuits in general, and what you see here, these images here are images of bosons and condensates trapped in optical potentials with a different shape. So, for instance, and the first row here, these are the optical potentials themselves. So these are light patterns that we use for atom trapping, and the second row are the actual images of the atoms in these trapping potentials. So we can have things like just a simple guide here, or we can have a guide with, you can see here it's quite small, a little junction here, or we can have a ring trap, or we can have this cross shaped trap. And all these configurations have their merits, but in this talk, I will focus on the ring trap. So that's what we have in the lab. That's pretty much the state of our experimental results. What I will show you for the rest of the talk is our future plans and some numerical simulations to go with them. And so what we really want to do in our ring trap is to generate superpositions of vortex and anti-vortex states. So basically, in our ring, we want to have vortices or persistent currents, which are superposition of a current going around this way and a current going around this way. So the motivation for this, there are two possible motivations here to begin with, which are these two papers, these two theoretical proposals. The first paper by Jonathan Dowling shows that if you can generate these vortex-anti-vortex superpositions, then you can do gyroscopy. So you can sense rotations. So this is a first motivation. And the second motivation here by Veronica Aufinger is using, again, these vortex-anti-vortex superpositions, but specifically to measure magnetic fields. I know it's not in the title of the article, but in the article they do consider specifically the case of are in the remit of quantum sensing. So using these states, these quantum states as sensors. So, okay. Now, let me step back briefly. And ahead of discussing how to generate these vortex-anti-vortex superposition, or this superposition of circulating states, I want to briefly review how you produce just one circulating state. And there are different techniques here, which have already been implemented in the lab or have been proposed. For instance, in this work here, they started with a ring-shaped boson condensate, and they produced circulating states by taking a barrier like this, and then moving the barrier around the ring and setting the condensate into motion. So we can call this the stirring method, because you're stirring your barrier around the ring. So this is a way of doing it. Alternatively, like done here, you can do phase imprint with a two-photon Raman transition. So this changes the internal state of the atom. You go from this internal state to this internal state with a two-photon transition. And the key point here is that the two beams involved in the transition, one is a Gaussian beam and the other one is a Laguerre-Gaussian beam, which carries angular momentum, carries orbital angular momentum. And this orbital angular momentum gets transferred to the BEC wave function. And we can call this a phase imprint because the phase of this field gets transferred onto the BEC wave function. So that's another way of doing it, phase imprint with a two-photon transition. Another way of doing it, shown here, relies on pulsing a beam of light that has a gradient of intensity that looks like this. So the blue thing here is the ring trap. And then, in addition to this ring trap, you pulse for a short time an additional laser beam that has this intensity distribution. So you see, going around the ring, you go from light to dark. So there is an intensity gradient. Now, pulsing this beam gives you a light shift, which is position dependent. And this changes the phase of the BEC wave function this way. So U is the light shift, which depends on the intensity gradient. Tau is the pulse time. And the BEC wave function, again, acquires this phase, which is a phase winding, again, because of this intensity gradient going around. So this is another way to have this imprint this phase winding and therefore create a circulating state. So you see, we can call both these two methods phase imprint because we imprint a phase on the BEC wave function. Here we use the phase of the light, specifically the phase winding of the Laguerre-Gaussian beam, whereas here we use a gradient of intensity of the light, but the result is same result. We imprint a phase on our condensate wave function. So now, once you have imprinted the phase and you want to probe the circulating state, then one way to do it, like shown here, is by using interferometric methods. Okay, so this is one circulating state. Now, we get more ambitious and we want to have a superposition of circulating states. So how can that be done? A couple of ways. As done in these two papers, this was experimentally done by using the two-photon Raman transition with the Laguerre-Gaussian beam, but having a temporal sequence where you have you just repeat it twice as a function of time, and you start from your condensate here before your pulse. Then from here to here, you achieve this circulating state or this vortex state by with the first Raman pulse, and this is the first Raman pulse, and the LG beam here has a certain phase winding that gets imprinted on the condensate, and then you perform a second pulse, which is this pulse here, and this Laguerre-Gaussian beam now has the opposite phase winding, and the result is a superposition of vortex states on the condensate. And if you look at the corresponding density distribution of your atom cloud, it looks like this. So this is a way of doing superposition states. Another way of doing superposition states was proposed by Dowling in this paper. This paper is the precursor of the paper I mentioned a moment ago about rotation sensing. So it lays the foundations of that. And in this proposal, you use one Raman transition, not a sequence like this. It's just one Raman pulse, and the two beams involved in the Raman pulse is the Gaussian beam here, and here that's the new thing. Instead of using just one Laguerre-Gaussian beam, we use a superposition of two Laguerre-Gaussian beams with two different charges, m and minus m. And if you do the numerics here, you will find, and that's what this paper showed, that by performing this Raman transition with the superposition of the two Laguerre-Gaussian beams like this, the phase, the wave function of the condensate acquires this phase here, and you see this e to the im phi is the phase of this Lagrangian beam, and this e to the minus im phi is the phase of this Lagrangian beam. Because we had a superposition of Lagrangian beams here, we also have a superposition of these phase windings on the condensate wave function. And therefore, we have put our condensate in a superposition of vortex and anti-vortex, or superposition of two opposite persistent currents. And this becomes, therefore, a cosine of m phi. And you see, going back to this density distribution, this is what you get if you take the corresponding density distribution of this, and this case is for m equals to 1 and minus 1. So a superposition of two vortices with the charge 1 and minus 1. So the corresponding density distribution of this is given by this. So in our lab, that's what we want to do. We want to implement this proposal. And therefore, to do this, we need to have control of our light fields. We need to generate these states. So how do we do it? How can we do it in the lab? So oh, I got frozen. Oh, I got it now. Good. So how do we do it in our lab? In our lab, we use computer-generated holography. This relies on this device here, which is a spatial light modulator, SLM. This is how we control both the intensity and the phase of the light, and that's how we can generate all the fields that I've just mentioned. So very briefly, how it works: our SLM is it modulates the phase of the light. So it's a liquid crystal-based device. We arrive onto this liquid crystal with a Gaussian beam coming from an optical fiber, for instance. And then the SLM is a device made of pixels. It is an array, a 2D array of pixels. And the output beam, the beam that gets reflected by the SLM, so this beam has passed through the liquid crystal and has passed through the liquid crystal, and then there is a mirror behind the liquid crystal layer, so that it also passes back out from the liquid crystal. And this beam now, at the output, has been phase modulated. So there is a phase modulation, a phase retardation coming from each of the individual pixels. So this is like a generalized diffraction grating, which is a phase grating, because it is the phase that we control. Therefore, to turn this into an intensity pattern, for instance, we need to work in the far field. And so you let the beam propagate. In practice, we put a lens on the beam and we look at the focal plane of the lens, which is in fact far field of diffraction. And this is our trapping plane. That's where our atoms will be. And for our experiment, we want this SLM to do quite a lot, actually. We want our SLM to provide us with a ring trap. That's the trapping potential. And at the same time, we want the same SLM to also provide us with the laser beams for phase imprint, so the Lagrangian beams. And so for this purpose, we want to use this device with more than one wavelength at the same time, because specifically here, just to give an example for rubidium, for instance, your ring trap could be something like 1064 nanometers, which is far detuned from the rubidium transition. And so I want a ring at this wavelength, and at the same time, from the same device, from the same SLM, I want our Raman beams, which need to be quite close to resonance, which for rubidium is 780 nanometers. So we need to control. So therefore, in conclusion, on this trapping plane, we need to control both the amplitude and the phase of the light. We need to control both because we're doing phase imprint starting from the phase of the light. So we need to control both amplitude and phase of the light. And we need to control to do this with two different wavelengths simultaneously. So, how do we do this? First of all, I know this is getting a little technical, but it's a useful thing to show very briefly. How do we control the two different wavelengths at the same time? So what we do is we can call it multi-wavelength holography. So controlling multiple colors with a single SLM. So let me give an example here. So imagine that our SLM here is just a simple diffraction gratings, with a well-defined period, so that this is the wavefront of light coming from our SLM. But we work with two different wavelengths at the same time. So we have a red wavelength, which is larger than a blue wavelength, so lambda 1, lambda 2, with lambda 1 larger than lambda 2. And then, as I said, we work in the far field. So we really work with what we can call a diffraction order. So this is the diffraction pattern that you get if you take this grating and you illuminate it with two wavelengths at the same time, so the red and the blue. See, in the center, you got the zeroth order of diffraction. Of course, the two colors are overlapped. But then look at the first order here and the minus first order here. There is a displacement between the blue and the red because the diffraction angle is proportional to wavelength. So the red spot is farther out from the zeroth order than the blue spot because it has a longer wavelength. But in our experiment, we want different wavelengths at the same point because we have our condensate, we want a ring trap there, and we want the phase imprint light there at the same point. So how do we do this? You see, the two spots here are not in the same point, they're displaced. The way to do it is go back to your diffraction grating, and instead of just having a period, you can put more than a period there. You can put two periodicities overlapped here. You can do that with the SLM, so that you have two different periods in your diffraction grating. And that means that if I go back here to the first order of diffraction, the blue spot becomes 2, because you have got two periodicities, and therefore you got two spots from the blue light. And the red light, the same, you're going to have two spots coming from the two periodicities. Now, you can arrange it so that one of the blue spots overlaps in space with one of the red spots. So that's what you can do. Let me show you a more visual example of this. So what you see here in the center, this is the phase on the SLM. So this is our generalized diffraction grating. So the SLM has this phase. We work in Fourier transform in the far field. So this is the Fourier transform. And you see, we calculated this phase so that in the far field, we do have two spots, right? Now, if you take this phase grating and you illuminate it with two wavelengths at the same time, each of the two wavelengths will produce these two spots. And that's what you get here. So if I illuminate this phase pattern with two wavelengths, one is blue and the other one is red. Blue is 780 nanometers, red is 1064 nanometers. You see, each of the two wavelengths will reproduce the two spots. And the 780 wavelength, the two spots are here. The 1064 wavelength, the two spots are here. And indeed, we arranged it so that in this area here, in this point of space, the red spot is overlapped with the blue spot. And that's what we wanted, right? So what is this now? Experimentally, this is the zeroth order of diffraction. So as in the previous slide, and you see, this is basically the center of your output plane, which on the calculated output, it's this here. So this is the center of the output plane, and you see, you design the two spots on the output plane with distances from the center, this R1064, R780, such that when you illuminate the phase pattern with the two wavelengths, you get this overlap. And because the diffraction angle goes with wavelength, these two distances here need to satisfy this relation in order to have this overlap. Okay, so that's what we do in terms of multi-wavelength holography. So Now, this was just for demonstration. Let's look at our specific case of ring and face imprint. That's what we want to do. So, and this is what we can do with the SLM. So, as I said, we need to control the intensity or amplitude of the light as well as the phase of the light for this experiment. So this is the target intensity that we need. And you can see here, this is our ring trap. And this pattern here, this is the superposition of two beams with equal and opposite phase winding. They do interfere, so the two LG beams will interfere, and this in corresponding this intensity distribution here is the interference pattern of the two LG beams with opposite phase winding. So, and let me emphasize again, they are the ring and the LG beams are in different positions on the output plane, because again, as we just saw, once you illuminate your hologram with the two different wavelengths, this will be a 780 nanometers. This will be a 1064 nanometers. You will get an overlap of the ring and of the phase imprint light. So they are displaced here, but they get overlapped when you illuminate your SLM with two different wavelengths. So, so this is intensity, and this is the phase. And in particular, let me show you here. This is the phase of the overlap of the two Lagrangian beams. If you overlap two Lagrangian beams, the corresponding phase structure looks like this. So it's pi, it's 0, pi, 0, pi. That's the phase structure of an overlap of two Lagrangian beams. So to produce this, we therefore need to get this phase. We need light that has this phase and this intensity. You're probably wondering what is all this mess around our ring and our phase imprint light. This is just a byproduct of our optimization algorithm. The intensities look very good here and here, and the phases look very good here and here, but this comes at the cost of putting noise everywhere else, and that's just so ignore the mess. It doesn't matter actually, because the important thing is what the atoms see. Which is the good regions. Okay. By the way, how we control phase and amplitude at the same time, this is shown in this paper. Therefore, in conclusion, we can program our SLM to produce a light field that has this intensity and this phase, and this will enable us to do this experiment where we have a Raman transition with the superposition of these two LG beams, according to the proposal by Jonathan Dowling. So now, if we simulate the evolution of our BEC after the Raman pulse, so after it's been put in a superposition of vortex and anti-vortex, this is going to look like this. So this is the time evolution, and in particular here you see there are two lobes of density. This is the density distribution of the condensate. There are two lobes around the ring. This is because the phase imprint was done with vortex anti-vortex with charges ±1, and this gives rise to the two lobes. And now what we simulate here is actually a rotation sensor. So if you apply, if you generate this superposition and then you apply a rotation, what you get is, as you can see, going from here to here to here, you get a precession of your standing wave. So you can interpret this this density pattern as as a superposition of two states, vortex and anti-vortex. So the two states interfere. So this is an interference pattern. It's a standing wave of atomic density. And this standing wave precesses over time after you, if you apply the rotation. And that's because, as you can see here, you start from a superposition of the two states, but if you apply a rotation, then each of the two parts of the superposition acquires a phase phi t, minus phi t here and phi t here. And there is a phase difference between these two phases, which is given by this. And this causes the precession. This omega, big omega, is applied rotation. And this is really similar to Sagnac phase. It's perfectly equivalent to a Sagnac phase. So by monitoring over time the precession of the BEC standing wave, you can measure your rotation. So check in time. Now, we can do this, but we can also do other things. For instance, we can decide to imprint something different on our condensate. So this example here is no longer a superposition of Laguerre-Gaussian beams. This is what we can call a phase grating. So we can design our phase imprinting light so that the phase looks like this. And if you go around the ring, the phase is given by these dependence. So cosine of gamma phi, phi is the angle around the ring. And therefore you see this is a periodical phase that you can imprint on your condensate. So it's like putting a diffraction grating on your condensate. This example here is for this periodicity gamma. This gamma gives the periodicity, which is equals to 2. So you go from minus pi to you go around. There's 2 periods of the phase winding here in this example, and this is going to be your BEC wave function after the phase imprint. So you imprint this phase imprint here on the BEC phase. And this is pretty much like a diffraction grating, but for matter waves, right? So for instance, we can simulate this phase imprint, and then we can look at how the wave function evolves after the phase imprint. So it equals 0. This is our BEC wave function at the time of the phase imprint. You don't notice very much here. This is a phase imprint, so it doesn't change the density distribution immediately. But you have imprinted that phase. So if you let the state evolve over time, you begin to see what really look like diffraction peaks. So it's like your diffraction pattern manifesting itself as you increase the time, a bit like light coming from a grating. After some propagation length after the grating, you begin to see diffraction peaks, and that's what we see here. And in this simulation, again, we applied a rotation so that there is also a precession of the pattern due to the rotation. So this can also be used as a rotation sensing. It's just a different way of doing a similar experiment. Then I'm coming to the final part of my talk, which I think it's a good thing because I'm probably running out of time already. So now we can be a little bit more creative in what we do with these optical traps with different geometries and phase imprints. So I think the examples I've shown you demonstrate that you actually have quite a lot of flexibility to engineer the state of your condensate. And this flexibility comes from the fact that on one side, you can change the shape of your optical trap. So you can change the density distribution of your condensate. So if you regard your condensate as having a wave function with an amplitude and a phase, the trapping potential will shape the amplitude of the wave function as a function of space. And with phase imprint, that is a very general way to shape the phase of your wave function. And if you put the two things together, you have, we could almost say full control of engineering the wave function of your condensate, both in amplitude and phase. And so to show how this can be used to create in yet another way these vortex-anti-vortex superpositions, this is just an example that uses a different, this is just for illustration purposes. Let's not worry about ring traps yet now. Let's consider all the way back from textbook quantum mechanics, a box potential. So this is our box potential in 1D. And let's say that I want to engineer my BEC wave function so that our condensate is not in the ground state of this box, but in an excited state of this box. So I want to obtain this as a final state. And the one I'm using here is the third excited state of the box. And so I want to put our condensate in this excited state of the box. So how would I do it? Well, it's a condensate, so I want to start. This is the final result, but I want to start from the ground state because it's a Bose-Einstein condensate. So the way to do it is by starting from a different box potential, which is a box, same box potential as before, but with barriers here. So we start with some barriers, put here, here, and here. And we call this potential V1 because it's different than the previous one. And here, this is our starting point. We produce a Bose-Einstein condensate here, and the wave function will look like this. So we have these 4 lobes. That's the ground state of the box. The assumption, and that's really important, is that these barriers here are tunneling barriers. So there is tunneling of atoms across the barriers, which ensures that there is just one phase. So there is the same phase of the wave function here, 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 and here. No fragmentation. This is just the ground state of the potential, and the phase is the same everywhere. So this is our starting point. We produce a condensate here, and then we apply this temporal sequence here, where we, at the same time, we suddenly remove the barriers. So you see the barriers are no longer here, but we keep the shape of the wave function because it's a sudden change. And at the same time as removing the barriers, we apply a phase imprint with our phase imprint beams, where you see the first lobe has got 0 phase, the second lobe gets pi phase, then again 0 phase, and then pi phase. And so we do this phase imprint, but a pi phase is equivalent to flipping the sign of the wave function there, and therefore we go from a positive lobe here and here to a negative lobe here and here. That's the result of the phase imprint. And then if you look at the overall shape of this final state, it is indeed the excited state that we wanted to achieve. So by doing this temporal sequence of phase imprint and dynamically changing the trap, we can put our atoms in the excited state of the box. It's almost like a population inversion. Instead of having all the atoms in the ground state of the box, we have all the atoms in one of the excited states. Now, what is the catch here? The catch is that in order to have good tunneling barriers, it's important that the wave function doesn't entirely go to 0 at the position of the barrier, and this will give you a fundamental discrepancy with the excited state that you actually wanted to achieve. So there is actually a non-vanishing. So we don't really have nodes here. We have a small but finite value of the wave function, and that's a discrepancy between the real implementation and the ideal implementation. But what we find in numerical simulation, that this works quite well actually. So this is the last thing before I finish. Let's now go back to ring traps, because you see, if I have a box and then I close the box onto itself, you get a ring geometry. So we can apply that idea to the case of the ring trap. And therefore that's your ring with the barriers to implement our scheme, and we apply a sequence where here suddenly we remove the barriers and suddenly we imprint the phase. So here we had our BEC was in the ground state of this ring plus barrier potential. So we have lobes corresponding to each sub sections of the ring potentials. if we remove the barriers and do the phase imprint, we still retain the lobes that we have from the start, but now the phase imprint is such that consecutive lobes have this phase structure 0, pi, 0, pi, 0, pi. And this is, like in the previous slide, this is now an excited state of the ring, like before we had an excited state of the box potential. And this excited state is indeed the vortex-anti-vortex state that we wanted to achieve. And once we have achieved this, we can let it propagate over time, and that's the time propagation of that. And the key point here is that the time propagation looks quite good. The lobes stay quite close to what it should be. There is no spreading. There is no, there is this is very close to the stationary state, which is what the ideal vortex-anti-vortex is a stationary state, so it doesn't evolve in time. And the fact that our state that we have created this way also doesn't evolve in time is evidence that we are doing a good job at creating that stationary state. There is a little bit of precession here again because we put a rotation in. Okay, so I realized that I probably used up enough of my time. So let's conclude here. So of course, from the numerical point of view, we can add atomic interactions. That's quite crucial because up to now, everything I showed you was no atom-atom interactions, so single particle physics. But of course, atom-atom interactions can increase, they can give you a rich system. And so it could be quite interesting to add to our simulations. At the experimental level, there will be challenges, no doubt. And finally, this maybe is slightly more technical points. I gave you all my examples based on a phase-only SLM because that's what I have in my lab. But in atomtronics, lots of groups are actually working with these DMD, digital micromirror devices, and this can also be used to achieve the objectives that I've discussed. So it's other ways of doing it as well. So let me finish by thanking the people who've contributed to this work. So, and thank you very much, everyone, for listening. Are there any questions?
So thank you for your very nice talk. And the session is open for questions. So first I will check on the YouTube. No, there is no question on YouTube.
So I have a question, Rosario Fazio. Sorry, can you, there is something I did not understand. So do you need, in order to have quantum mechanics in this superposition of current states, you need to have interaction between the atoms, right? I mean, as far as I understand, these are static situations, right? So in which you have a superposition, but there's no quantum dynamics associated to this superposition of states of supercurrents. Do I understand correctly, or?
So in our simulations, we just put the atom-atom interactions to 0 for simplicity. Of course, they can always be added, and then experimentally, you will have them for sure. If you work with rubidium, you have the scattering length of rubidium. But at the fundamental level, I would say that you can have you can have these persistent current states and superposition of persistent current states. You don't need atom-atom interaction to produce these states in the first place.
Yes, so you're right. What I meant is the following: if you take the similar example in the squid, okay, so there you can have superposition of supercurrents, right, going clockwise and anti-clockwise. But in order to put some dynamics, quantum dynamics, they need to put capacitance and things like that, charging effects. And I was wondering if something similar should be done here.
Yes, if you add atom-atom interactions, you will definitely do more physics. from the strict point of view of doing rotation sensing, you do not need atom-atom interactions. Okay. So everything, this idea of Saganac phase is there anyway. But yes, to work with the squid setup and the Josephson junction, then obviously atom-atom interactions are crucial there, and then going, for instance, from the squid experiment to the flux qubits, there you need correlations. So definitely need atom-atom interactions to the level that you have these correlations and you go beyond mean field. So therefore the steps here are, well, first of all, we should put in some mean field, obviously, to simulate atom-atom interactions. And then if you go beyond mean field and you look at correlated states, then you open up a lot more.
Okay, thank you very much.
Okay, let's see if there are more questions. No, this is not the case. So I thank the speaker again, and I would move to the next speaker, that is Mirko Consiglio. Well, I suspect that Mirko is having problems because he just wrote something on YouTube. So while we solve his issues, we could maybe make a switch with Roberto Tricarico if he's connected. Roberto, can you hear me?
Yes, sure, I'm here. Just 1 second. Here we go.
Okay, maybe we can start your presentation.
Yeah, no
and, we try to solve the problem of Mirko.
Perfect.
Okay.
No problem.
So Roberto Tricarico will give a talk about transient dynamics in Rydberg EET. So please.
Yeah, I share the screen. Just
Okay.
You see it?
Okay. Okay.
Okay. So just 1 second. Okay, here we go. So, everyone, I'm going to talk about transient dynamics here in Rydberg EET. I also want to thank the organizer for this nice conference and for the 3 days in Naples I attended here. So, this is something I started to work on the supervision of Professor Derek Chang in January 2019. And then together with him under his supervision, we developed the theory for an experiment in the group of Professor Derek Matten. And we developed this, the final product is this joint theory experiment paper together with where I developed the theory part and the supervision on Derek, and Auxi developed the experimental part. So before telling you about our research in particular, since this is a pretty general conference about quantum technology, I want to be sure to give you the general picture about what we do, and then I will devote just the final 30% of my talk to this specific work. So photon-photon interaction is the first concept to understand. So when we want to process the information, we need interactions and among photons, but photons in linear media do not interact with each other. And the optical materials that we have at our disposals in general exhibit nonlinearity only at high power. From the quantum viewpoint, high power means many photons. So our first question is, how can we bring nonlinearities down to the few photon level? How can we reach and control the so-called quantum nonlinear optics regime? So a possible answer is to use single atoms. Let me be more clear about it. So imagine that you have an atom, so you have a not uniform spacing among the energy levels. And this makes an atom shine by a laser at a given transition frequency as a two-level medium. And with a two-level system where we can identify a ground state and an excited state. This object is extremely nonlinear for the easy concept that I'm going to show you, which is basically imagine that the first photon comes and excites the atom. The atom absorbs the photon and gets excited, but now if another photon comes, the second photon cannot be absorbed, right? So this is a blockade phenomenon. And that's something extremely nonlinear if you think of it, because if we consider the single atom as a system, this system experiences a completely different response if we send one atom or two atoms. The problem is that in real life, the interaction probability between the photon and the atom is extremely low. And so what happens in general is that even if the atom is excited, other photons will just pass by without interacting with it. And so we keep on measuring. We do not detect any nonlinearity. Adding more atoms, however, it is not a solution, because it is true that if we consider atomic ensembles, we increase the probability of the photon atomic ensembles interaction, but we won't measure nonlinear response in any case, because now photons can approach different atoms, excite different atoms, and then decay back and emit photons. So this is where the problem is the following. Since it is true that every two levels object is nonlinear, is something extremely nonlinear, but this nonlinearity is local in space and narrow in time. So what do I mean with that? It means that to measure nonlinearity, we need two photons to approach the same atom within the lifetime of the excited state, which is pretty short, 20-30 nanoseconds. So the point is that here is where Rydberg atoms comes into play, to break this kind of spatial-temporal constraints and to help us in detect nonlinearity. So let me tell you what do we mean with Rydberg atoms. So let's consider an atom, and these are the energy levels of the electrons. You see that the spacing is not uniform, and we all know that as we approach the continuum, the free electron limit, all the levels get close and close to each other. The final levels are called Rydberg levels, and a Rydberg atom is an atom where an electron has been excited up to these levels, up to one of these levels. Rydberg levels have interesting properties. In particular, they have two features, which are the long lifetime and huge dipole momentum. Long lifetime, why do I mean long lifetime? Because we're talking about a lifetime that can be in the order of hundreds of microseconds, while if you take the lifetime of first excited states, can be 20-30 nanoseconds, for example, just to give some numbers to have an idea. And then they have a huge dipole momentum. Thanks to these two features, basically, we can build a blockade mechanism that is non-local in space. And so we want to use these two features to break the nonlinear constraint to detect nonlinearity. The principle is very simple, and we can consider now atomic ensembles where we have Rydberg atoms. Now, when the first photon comes and excite an atom, now once that the atom is in a Rydberg level, what happens is that the big dipole momentum of this level interacts with the surrounding Rydberg levels, generating an electrostatic potential that has the effects of shifting this level to infinity and decoupling them from the incident transition. So what happens is that when our other photon comes, this other photon cannot be absorbed. And this is again a blockade mechanism. But now this blockade mechanism allows us to detect nonlinearity. Why? Because we do not need two photons to approach the same atom within a short interval of time. To detect nonlinearity, we need two photons to approach the same blockade sphere. This is called the blockade sphere, and this is the radius is the blockade radius. To approach the same blockade sphere within an interval of time that is pretty large, because it's the lifetime of a Rydberg states. It can be hundreds of microseconds. And also the blockade sphere is pretty large. We're talking about micrometers. So 4 order of magnitude bigger than an excited state atom. That's why sometimes we refer to Rydberg atoms as superatoms, let's say. So the point is that we understand in this way how Rydberg atoms can provide us a blockade mechanism, and how this blockade mechanism means essentially nonlinearity down to the few photon level, and that we need nonlinearity to induce photon-photon interaction. But we have to be more precise about what we mean with nonlinearity. From the classical viewpoint, something is nonlinear when you have a nonlinear relationship between output and input. In the quantum world, or at least in this concept, it is useful to define nonlinearity in the following way. We have to resort to the concept of the G2 function, the normalized second-order correlation function, which is indeed the ratio between capital G2 and the square of the intensity. Besides the formal definition, it can be understood as the ratio between the two photon detection and the single photon detection. So what do I mean? I mean that we can classify light according to the value of the G2. The G2 can be smaller, equal, or greater than 1. It's always greater than 0. Greater or equal than 0. And essentially we call anti-bunched light the light where the G2 is smaller than 1, coherent light when it is equal to 1, and bunched light when it's greater than 1. If you look, for example, at coherent light, which is in general the light produced by a laser, here you having a G2 equal to 1 means that if you detect light at some instant of time, you will have the same probability of finding single photon or photon pairs or photon couples. That's the point. When you have a G2 greater than 1, you will be more likely to find photon couples G2 smaller than 1, you will be more likely to find single photons. So essentially, these G2 functions give us an information about how photons like to travel, if alone or in groups. And now it is useful to define a nonlinear quantum system down to the few photon level as a system that is able to turn coherent light into anti-bunched light. So we enter with a light ray laser with a coherent light G2 equal to 1, where I have the same probability of detecting single photons or two photons. But then after the interaction with the system, I find anti-bunched light, which basically means that I'm more likely to find single photons. And this is extremely nonlinear because this kind of systems reacts differently in principle to the single photon component and to the two photon component of the incident field. And this is the basic principle where the kind of system that we want to build using Rydberg atoms. Before doing that, I have to recall you some basic concept about scattering by atomic ensembles. So imagine that you have an ensemble of atoms, so two-level systems, let's say, and then you have a probe laser here, and then you have we refer to the transmission, so the light on the other side of the ensemble. Set omega p the frequency of the probe laser. We can change it and tune it on the transition or being very far. This is called the detuning. The detuning, so it's the difference between the frequency of this laser and the frequency of the transition. As you can imagine, when you are far detuned, so you are in this kind of regime, the medium is transparent because the photons do not interact with the atoms, of course. But as you get closer to zero detuning limit, the transmission goes to zero. And in particular, at zero detuning goes to zero like e to the minus optical depth, so exponentially. The optical depth is a parameter of the ensemble, which can be thought as the product between the number of atoms and the atom-photon probability interaction. And essentially, this kind of absorption here is due to the fact that when we have the interaction, when the laser is tuned on the transition, it excites the atom, but then the atom decaying can re-emit a photon in every direction. So it's very unlikely that the photon gets re-emitted in the forward direction, as that's why the medium appears absorbing. Okay, so first concept is that the two-level medium is absorbing at zero detuning. Now, second concept, let me introduce you this phenomenon that is called electromagnetic induced transparency, EIT, what we call EIT. So it's a three-level system phenomenon. You have to think this way. You have a ground state, then you have a probe laser that couples the ground state with the excited state, but now you have a second laser that we call control field, that couples the excited state with a third long-living level that in general we call storage level. What do I mean with long living? A level that has a lifetime that is much longer than the typical time scale of the experiment, while your excited state is lossy. So this kind of losses can be detected in the experiment. So what happened? Between these two fields, there is a destructive interference that make your population in the excited state zero. So when the atom is excited, it directly goes from ground state to the storage level, which is lossless at the time scale of the experiment. And so if now you consider this kind of setup, so you have the same atom as before, but now plus the probe field from which you send the photons, you also have a control laser that shines the whole ensemble. What happens is that in the region of absorption, the transmission now goes to 1. It opens, a transparency window gets open. This transparency window has this expression, this width. So it is proportional to the Rabi frequency of the control field, which is omega c. And now we can understand that if we send through the ensemble a light pulse centered at zero detuning and with spectral components within the EIT bandwidth, the light can travel through the ensemble at this group velocity with a delay time of given by the EIT delay time. This is this kind of expression. So it can pass through the ensemble. This is interesting because a two-level system is absorbing, but now if you add another third living level, now the system becomes transparent and the light can pass through it as soon as the frequency components of the incident field are inside this bandwidth. Now that we have this concept, we can understand how can we use Rydberg atoms to build the nonlinear system that we want. And this is something that has been proved in 2012 in this work. So basically, we talk about Rydberg EIT. Rydberg EIT is EIT where the third level is a Rydberg state. This is extremely important because from the single photon viewpoint, this is standard EIT. So the photon simply will pass by through the ensemble because of the transparency, a single photon. But now photon couples will happen. They encounter troubles. Because two photons cannot excite two Rydberg levels within the same blockade sphere. So this system in principle is something that can allow single photon propagation and can stop can inhibit photon pairs propagation. That's the thing. And you have to think of it this way. In this paper, they consider steady state. So the laser is a continuous wave of light, is always on. And as you can see here, before approaching the ensemble, you have the same probability of detecting the photon pairs or single photon. Pairs, photon, pairs, photon. But after the ensemble, you find photon, photon pair, photon, photon, photon pair. So you will be more likely to find single photons instead of couples, because this system suppresses the couple propagation. Okay, the photon couple propagation. That's the thing. Now, they also proved that this mechanism can be improved if we increase the optical depth or if we decrease the amplitude of the control field. Now, what's the point? In principle, we would like to have a G2 equal to 0 because it would mean to have exactly a train of single photons as output. But the point is that to approach this kind of 0, as you can see here, you have to go to high optical depth, for example, or to reduce omega c. This is something that can be done. However, it has some experimental drawbacks. For example, having an higher optical depth means to trap more atoms. To trap more atoms, I need to enlarge the transversal cross-section of my laser. And it means that I need a blockade radius larger than this new transversal cross-section, which is something that I might not have, for example. Or reducing omega c is something useful, possible, but if you reduce omega c, you reduce the delay time. You increase the delay time. So you increase the time the information needs to travel through the ensemble. And so other mechanisms, for example, the dephasing can pop in and you will simply lose the information. And that's why what they do in Professor David Matten's group was pretty much interesting, because they consider, instead of continuous wave light, they considered pulse light. This is not the only work. Also, there is another group in Charles Adams' group that worked on the same topic. They found that the G2 function is not constant along the pulse, but it varies. So what does it mean? It means that the steady state value, it is not a fundamental limit, first thing, and then that that the G2 can be smaller than the steady state value. For example, this region. So we have some regions that are more anti-bunched than the steady state light. And this gives this idea, for example, of new protocols to turn light from classical to quantum, which basically means instead of considering continuous wave light, we can send light pulses and just retain the final end of the pulse. This will give us the chance to have a smaller G2, which means more nonlinearity, but with the same optical depth, with the same omega c, that is to say, with the same experimental resources. That's the thing. So in this paper, we studied this rectangular case, also triangular case. We did a complete theoretical analysis of all the phenomena. Of course, I don't have time to go through all of that, so I decided just to show you how we can explain an example of our theoretical analysis of how can we explain this extreme anti-bunching at the end, why the G2 approaches 0 at the end of the pulse. So this is just basically the main goal. And so I will travel now, the last part of my talk, I will simply discuss this final tale from the theoretical viewpoint. How can we understand it? Because look, there is really no easy way to look at it, because the G2 is normalized to the intensity. So it's not that because the intensity is going to 0, you can justify the G2 approaching to 0. You really have to move beyond linear analysis and approach a nonlinear analysis. So let's start by observing that we are working in the weak driving regime. What do I mean with weak driving? So imagine that you have the quantum states of the atoms. It can be written as the ground state. Then you have a first a single excitation subspace, a double excitation subspace, and so on. So what do I mean? I mean that here I can have a single atom excited. Here I can have 2 atoms excited, 3 atoms excited, and so on. When you are in weak driving, basically the population of a given subspace, for example, this one, is way bigger than the population of the following subspace. And so basically I'm allowed to truncate this expansion up to the order that I need. For example, in this case, we are studying second order correlation, so I need at least psi2, and I can truncate my expansion here. Because the effect of the higher order subspaces is negligible. So this is the first thing to observe. Then we can make, for example, some useful limits. Another thing. And then here, this kind of components of the wave function is made of 2 terms, which is this one, psi e and psi r, which means a single atom is in the excited state or a single atom is in a Rydberg state. And then the 2 excitation component can be 2 atoms in excited, 2 atom Rydberg, or 1 atom excited and another one Rydberg. Now we can perform some limits to, for example, to give to reach the core of things. And for example, we can consider the infinite blockade radius. So where we do not allow two Rydberg occupation within the ensemble. So a Rydberg radius bigger than the whole ensemble, let's say. And then we can, for example, consider the non-defacing limit. Okay, of course, we can do all the calculation also including finite blockade and defacing, but if you want to study the principle of the phenomenon, there is no need to do that. When you want to work on the experiment and derive some real simulations about the experiment, then you consider all these other technicalities. So if we make this assumption, the energy level scheme can be made this way. The population is this one. So we have the ground state, excited, Rydberg, excited, Rydberg, excited, excited. And we can see that this one is the single excitation subspace, and this is the double excitation subspace. And the two subspaces just talk through the probe laser. Now I want you to notice that I put the arrow just in upward direction. This is because since we are working in the weak driving regime, basically the single excitation subspace evolves independently, and then it acts as a source for the double excitation one. It feeds the double excitation one. So that's an idea. Now, the thing, what do we notice? If they talk only through omega p, we can think of another scenario which will simplify our analysis, which is the instant shut-off case. So we consider, instead of switching the probe field continuously off, we consider a step function. In this way, we start from a steady state initial condition. Then instead of continuously switching it off, we immediately switch it off. In this way, we can study the final turn off, the final transient, more easily because the two manifolds evolve independently. So we can study the single excitation and the double excitation subspaces independently from each other. And then from these two analyses that are easier than the coupled analysis, we can rebuild the original G2 as the ratio between capital G2 and the intensity square. So that's the strategy. Let's start with the single excitation subspace. What do we do? Okay, this is standard EIT basically, because here we have no blockade phenomenon in this kind of analysis. And so basically this is just retrieving from a quantum memory. So we know that in steady state you have this...
Roberto, sorry to interrupt you. You have just 1 or 2 minutes. Sorry.
It's 2 slides. Okay, so then you have this square pulse, and then when you retrieve it, you find this smooth output, and this is because you have a finite bandwidth. So since this is standard DAT, we expect this retrieving time to scale as the AT delay time, and indeed it is confirmed by the experimental measure, by the numerical experiments. Then when you move to the two excitation subspace, you do the same thing, and you compute the retrieving time in this other case, and you find this interesting feature. So that as soon as the optical depth is big enough, the output delay time do not depend on the optical depth, but it scales like 1 over optical depth. Okay, and this is interesting because this is the trademark of the trace of super radiant behavior, because it means that all the atoms are phase matched, and then they emit constructively in the forward direction, leading to a decay rate that is faster than the single atom one. When you plug these two ingredients together, then you find that you have constant of time that scales like optical depth for the denominator of the G2. Then the numerator scales like 1 over optical depth, and you can justify the G2 going to 0 simply because the numerator and denominator both go to 0, but at 2 different time scales. So this is just an example of how can you perform this kind of analysis, and in the paper you will find all the details of all the other regime and other experimental situations. Thank you very much.
Okay, Roberto, thank you for your talk. And let's see if there are questions on the web. Okay, doesn't seem to be the case. Maybe I have a curiosity more than a question. Do you think it is possible to include also, because if I understood correctly, you are modeling everything as two-level systems.
Yeah.
If you have also other excited states, is there a way to include also the role of these excited states in renormalizing these dynamics, or do you think that it's completely irrelevant?
No, I mean, yeah, basically we model, you mean Basically, we mode it's a 3-level ensemble, actually, not 2-level. You mean if you have two kind of excited states?
Yes. Suppose you have also other excited states in the real atomic systems. Could you take into account also the effect of desired states on your dynamics, or do you think it's irrelevant?
No, I think that well, yeah. I mean, from the theoretical viewpoint, of course, from the numerical viewpoint, this is not a problem. You mean if it's irrelevant? Of course, to manage this kind of system, you need to be extremely precise. It's not that easy. You have to select the Rydberg state properly. And indeed, this is something, I mean, Rydberg atoms are something pretty much old, but only in recent years we have the technology to be that precise. Yeah. In general, you have to care about the frequency component of your input pulse. That's the thing, because if it is I mean, if there's a component that it's well inside, you know, the density of state of the atom, I guess that you do not interact with other excited states.
Okay.
Of course, if you send full pulse, yeah, in this case, it would involve other states.
Any frequencies, and so you
but
can.
In general, if you plug real numbers, I mean, for example, here you can see that your detuning, your medium becomes transparent as soon as you go, I don't know, more than 5. So you have to think you can take this guy as a reference. If you are within the bandwidth, everything is perfect. If you have, of course, if you start to involve other frequencies, you have to take into account them. But you can see that from this plot, for example, that it is completely transparent if your detuning it's I don't know, bigger than 5 times the lifetime of the experiment. So you can really plug numbers and see if
okay,
it's you have to care about it. But for sure, if you do not care about, if you do not give the right attention, you can have problems.
Okay. Okay, thank you for your answer, and there are no questions from YouTube. So also thank you for your nice talk, and so we can move to the next speaker. Bye, Roberto. I think that Mirko is here now.
Yes, I am here.
Okay.
Let me share my screen.
We can move to Mirko Consiglio, that is proposing a variational quantum eigensolver for SUN fermions.
Okay.
Actually, I cannot see. Okay.
Can you see? Okay.
Yes, I can see your presentation.
Okay. So okay, I can start.
You could please hide. Okay, that's fine. So please.
Okay, so hello everyone. I'd first like to thank the host for inviting me into this conference, and I am very pleased to be here. So I am Mirko Consiglio, and as my name would suggest, you think I am Italian, but in fact I am Maltese. And well, you could think that Malta compared to Italy is so small that it practically can be considered a quantum object. So apart from that, these are some of the colleagues that I have worked with on this particular project, of which now I will discuss, which is the variational quantum eigensolver for SUN fermions. So before I go into what I did in this project, I'd like to go through a brief preamble to just define a bit what the problem is, right? So currently, as John Preskill defined in 2018, we are currently in the era of NISQ devices. So NISQ standing for noisy devices, meaning that usually when we talk about a quantum computer, we have imperfect control over these qubits. Intermediate scale, stating that the amount of qubits that we have is around 50 to 100 qubits in the device. And well, quantum, I hope everybody here knows what that is. So to improve on these features, meaning to reduce the amount of noise or errors that we have in a quantum computer and increase the number of qubits, there have been many proposed theories and practices, mainly to try and lower the amount of gate errors, specifically in gate architectures. Also, techniques of quantum error correction are being developed, and even just look at different quantum computer architectures. So with that out of the way, let's delve into what is a variational quantum algorithm. Well, essentially, it's a quantum algorithm that's basically a hybrid one. So part of it runs on a quantum computer, part of it runs on a classical computer or a normal computer. The idea is to input a set of parameters theta, which are then passed into a parameterized quantum circuit, which does some unitary gates, which applies some unitary gates to our starting input state. And then you measure some or all of the qubits you need so that you obtain either an expectation value over all or some of the Pauli strings, for example, that you want to measure, usually building up to a certain Hamiltonian. And this is fed into a sort of objective function, where this objective function is then minimized on a classical computer so as to try and obtain some sort of value. And this is all based, of course, on the variational principle in physics. And so we can, for example, apply this idea to a variational quantum eigensolver, which when looking at fermions, for example, although this of course can be extended to bosons and other particles, the idea is to try and find the ground state of a specific Hamiltonian and respectively its energy. So generally, the structure of a typical VQE is as follows. The first thing you need to care about is the type of fermion to qubit encoding that you want to use so that you can transform fermionic statistics into those which the qubits obey on a quantum computer. After you decide on this encoding, the next step is to choose your variational ansatz, or sometimes also called the parameterized quantum circuit itself, which is usually an expressible enough variational circuit that is able to search through most of the subspace or the entire space of the Hilbert space needed to find the ground state. Finally, there exists many techniques on actually measuring the expectation value related to some sort of Hamiltonian, be it a Hamiltonian which is found in quantum chemistry or physics in general. And finally, the choice of optimizer used in the classical loop to determine the minimization of the expectation value or the cost function. And initially, most of this work has been primarily inspired from a paper by Cade et al. On solving specifically the two-dimensional SU2 Fermi-Hubbard model. So to go over what I'll be talking to you today about is, in this paper, or the manuscript we have developed, the idea was to first implement an n-component extended Jordan-Wigner transformation so that SUM fermions can be written in terms of qubits or spin 1/2 systems. Now, when we think of n component fermions, I'll discuss it next slide so that you get a better picture. The idea was then to look at this SUN Fermi-Hubbard model by simulating it with threaded with a magnetic flux and in a closed loop. Finally, the parameterized quantum circuit we looked at was initially meant to be quite shallow, yet also number preserving, so to impose a certain symmetry in terms of spin conservation. And finally, the analysis of a mesoscopic quantity called the persistent current with VQE was investigated. So what are SUM fermions? Well, in reality, these are some quite exotic particles. However, they have been experimentally realized using ytterbium atoms and even some other alkaline earth materials. And the idea of this is that instead of the typical n components you would have in terms of the spin, it's actually the nuclear spin that's being regarded as having the n components. So these SUM fermions can be used to investigate, for example, symmetry-protected topological phases, or even mesoscopic scale atomtronic circuits, which can ideally, in the future, hope to widen a bit the current quantum simulations we are now undergoing. And finally, what we investigated in this project was to cover matter wave circuits and probe different quantum phase transitions via the mesoscopic quantity known as persistent current. And what this SUN mapping does, or what we did, was extend the typical Jordan-Wigner transformation, which is applied to spinless fermions, but instead applying it to n spin components into the SUN fermions. So typically you would get L SUN fermions mapped into NL qubits, which can cover a Hilbert space of up to size 2 NL. So this can exponentially grow to be quite a large Hilbert space. So the model itself can be visualized as follows in this figure. As for an example, I show an SU3 5-site model, where the Hamiltonian is what you would expect from a typical Hubbard Hamiltonian. The T here corresponds to the hopping term along with the fermionic annihilation and creation operators, along with the magnetic flux term given in terms of phi attached to the hopping terms. Next, the U term is the on-site interaction present between different fermions on the same site with different spins. And finally, the V term is nearest neighbor interaction terms between fermions of the same spin or different spin. So, and finally, N is the number operator you would generally find. So after applying the Jordan-Wigner mapping, which is given in terms of this equation, and changing the indices of the site I and the spin color S to be in a one-dimensional index form, the Hamiltonian transforms into this equation here, where the only thing that's essentially different apart from the ladder operators and Pauli Z terms is just this P term, which is related to a simple parity dependent on the indices I and S. So given that now we have seen our Hamiltonian, how do we define the persistent current? Well, once threading the model with a magnetic flux phi and using the Pearl substitution, essentially the persistent current, specifically at zero temperature, is given by just partially differentiating the Hamiltonian with respect to the magnetic flux and then looking at it in terms of the ground state. So initially what we need to find on the quantum computer is the ground state of the Hamiltonian I showed you, and then we can compute the persistent current once we have achieved this particular ground state. So that's the first thing about the fermion to qubit mapping and the Hamiltonian. Now, what about the ansatz? Well, as I said, the idea is to produce a shallow yet number preserving ansatz. By number preserving, what I mean is that if we start in a potential spin configuration, we wanted to make sure that we end in that particular configuration. So no creation or destruction of fermions without us knowing about it, essentially, unless there are errors, of course. And the idea is this represents the closed system bounded by the atomtronic circuit. And so we had to implement these gates, the first one of which is the I-swap gate, which is responsible for hopping fermions between one site and another. And finally, the controlled RZ and RZ gates here represent the nearest neighbor interaction term and the on-site interaction term, respectively. So finally, once we combine all of this together, which is located in this figure here, the dashed box, this contains one layer of our parameterized quantum circuit. So first the hopping, followed by the on-site, the nearest neighbor interaction, and then the on-site interaction. And finally, for our particular spin configuration to be chosen, for example, in this case, we have one spin of color blue, let's say, one spin of color red, and one spin of color green. And so with this specific set of gates, we make sure that we end in that particular spin configuration as well. So this is how the VQE is implemented in terms of a gate architecture quantum computer. So when looking at a quantum circuit, typically the next question you ask, okay, so how complex is this circuit? Well, generally, we know that 2-qubit gates are more erroneous than their corresponding 1-qubit ones. So let's, for this simple case, ignore 1-qubit gates and their errors and only look at the 2-qubit gate decomposition of an I-swap gate and the controlled RZ gate, which in terms of many basis gate requirements decompose into 3 C0 and 2 C0 gates respectively. And we'll also look at the specific parameters. When considering that we have N spin colors and L sites, these are the decompositions with respect to each hopping interaction and 1-qubit sublayer, with the totals given here in terms of C0 gates, the depth of the circuit, and finally the amount of parameters, all of which scale linearly in terms of N and L. And finally, the results which I'm about to show you were all run on Kibo simulators, which is a Python package, and using a BFGS classical optimizer to optimize the parameters. So some of the results that I would like to show you are first here, where we looked at primarily the first instance of N greater than 2, so 3. We looked at 3 sites, so this corresponds to 9 qubits, and commensurate filling, so meaning that the amount of spins is equal to the amount of sites that there are. And in this case, we modified our parameters u and v with t kept to 1, just as a reference point, in terms of the magnetic flux phi. The first three, the top 3 images show the energy, the ground state energy, and the bottom 3 images show the corresponding persistent current. And each of these 3 columns respectively represent 3 different phases. One which is the metallic phase, the other is the mode phase, and the another has a particular beat phase. So for low U and V, we can see that even after just one applicable layer of the VQE, most of the persistent current and of course the energy is captured correctly when compared with the blue lines, which is the exact diagonalization. However, as soon as we start to increase U and then suddenly increase V, we notice that the more layers are required to properly capture the form of the ground state. And this is especially so in the last one, in the particular beat phase, where even just the first and second layers, that is the red and green, do not even showcase the shape of the waveform by the beat phase. However, once we go into 3 layers, immediately they align perfectly well with the theory. So this falls in line that given particular ansatz, we need to have it expressible enough so that it captures the ground state. However, we wanted to question further and look at why 1 or 2 layers are not enough. And in this case, we look towards an entanglement entropy, which can be shown to correlate with how expressible our particular ansatz is. So we took the entanglement entropy between half of the qubits and the other and compared it with these bipartite sets. In figure A and B, there is SU3 and SU4 commensurate fittings, respectively, for different phi. And in figure C, we looked specifically at the points where phi is close to 1/2, and then compared it with the number of increasing layers. And we noticed that for when considering a simple SU2 model, immediately there is no particular entanglement between one spin color and the other. However, once we looked at SU3 and SU4, we could notice why 1 or 2 layers weren't enough. We required more and more layers so that the entanglement entropy could increase and searchable enough Hilbert space could be identified, and so the ground state could be found, which is then where we could actually get the figure for our persistent current correctly. So to conclude, essentially, the idea of this work was to analyze a mesoscopic quantity, which is the persistent current, via the variational quantum eigensolver, and hopefully we provided a new means of investigating these new quantum phase transitions on near-term NISQ devices. So the next idea of this work would to actually be to simulate these on an actual NISQ computer by implementing various techniques, to minimize noise, such as stochastic gradient descent, circuit optimization, noise tailing, and there's also measurement mitigation techniques, etc. And ideally, we'd also like to look at more interesting mappings, let's say, rather than just extending the Jordan-Wigner to cover n components. There could be n extensions of mappings such as the Bravik-Kitaev, Bolfer-Chirac, or even custom encodings. So what I would like to conclude is that the manuscript of this work can be available, is available on arXiv via this link. These are some of my references that I used. And I would like to thank everyone for your attention. And if you have any questions in particular, let me know.
So Mirko, thank you for your nice talk.
Thank you very much.
Well, first I will check if there is some question raised on the YouTube channel, but there is not any. Well, actually, I had a question, but you mentioned it in your conclusion. So I don't know if you have an answer or not, or if it's an open issue. I was asking myself if things change if you apply Bravik-Kitaev mapping instead of the one that you use. Do you have some ideas of what could happen in that
case? So thank you for the question, first of all. And the general idea is that, of course, these are not the Jordan-Wigner where you just try to as simply turn the annihilation creation operators of fermions into just ladder terms. When you look at Bravik-Kitaev and Bolfer-Chirac, there are ways in which you could extend them, I believe. However, the most important problem to look at would be how to convert these transformations into sets of gates that preserve the the spin conservation, right? Because the problem is that the gates are straightforward to implement because of the simplicity, let's say, of the Jordan-Wigner. However, when looking at, for example, Bravi-Kitev, it's not so straightforward. And the gates which would need to implement to preserve that symmetry would be much harder to identify. So that is one reason why, as we have not looked at it into great detail as of yet.
Okay, okay. As far as I know, the IBM group has recently released some generalized Bravi-Kitaev for even maybe for SUN Fairbanks.
That's usually the problem, yes, because what we have found is mainly for SU2, the encodings and etc. And SUN is quite a recent subject, let's say, or an exotic subject, and there's not as many mappings, especially on quantum computers, as you would find for SU2. Yes,
I see. So thank you for your question, for your answer. And since we have no more questions from YouTube, I thank all the speakers of these sessions. Thank you, Mirko. Thank you to all the others. And well, now we have a virtual coffee break, and we should recombine at 4:05. So see you in 15 minutes, more or less. Bye.
Bye. Thank you. Bye.
Bye. Thank you.
C'è nessuno? Pronto?
Sì, salve Pasquale, sono Procolo Lucignano.
Ah, ok.
Fra qualche minuto incominciamo. Se vuoi provare la presentazione intanto.
Sì, perfetto. Ora dovresti vedere te stesso, ma andiamo al talk. Eccolo qui. Ci siamo?
Sì, perfetto, funziona tutto perfettamente.
Perfetto. Ma io lascerei così, poi mi dici quando iniziare.
Sì, va benissimo, giusto per stare nei tempi per chi si connette apposta per sentire il tuo contributo, ecco.
Ok, mi dai quando mancano 2 minuti, mi dici qualcosa? Come funziona?
Perfetto, sì, quando mancano un paio di minuti ti posso contattare, sia scrivo una cosa nella chat o dirti una roba a voce, come
No,
preferisci.
sì, a voi.
Okay, we can start with the last session of today. We have Professor Pasquale Calabrese from SISSA that will give a talk on symmetry resolved entanglement. So, okay, you can start.
Yes, I would like to start by thanking the organizer for giving me the opportunity to talk here, even if I'm just talking remotely. And I will discuss in this talk symmetry resolved entanglement in many body systems. And the goal of the talk is just to convince you that symmetry resolved entanglement is something interesting to be observed in this many body system. Let's just start without further ado, since we have very short time. So what is the entanglement? Okay, maybe it's completely superfluous in this context, but just to fix the exact kind of entanglement I'm talking about, let's think to a pure state, so no mixed state. We consider a bipartition of the Hilbert space, and usually this state is not written as a product state. So there is some entanglement between the parts of the system A and B, and this can be quantified by the von Neumann entropy of the reduced density matrix, which is minus trace of rho A log rho A, which is well-known entanglement entropy. And we will make use in the talk also of the Rényi entropy, which are just defined as the logarithm of the moments of the reduced density matrix times some factor. And you know that you can obtain the von Neumann entropy as limit of n that goes to 1 of the Rényi entropies, which usually in my context is called the replica trick. But okay, this is not really fundamental. What is the object we want to study now? Okay, we want to consider a many body state psi, which is symmetric under the action of some charge q, which means that the density matrix commute with this charge q. We consider a charge that is local, like can be the number operator in a fermionic system or a spin component in a spin system. Okay, and by local in particular means that it can be written as sum of different parts we are bipartiting the system, like q is equal to qa plus qb. When this happens, by tracing the over b the commutational relation, one obtains that even the reduced density matrix commute with the charge restricted to subsystem A. The fact this commutational relation implies that rho A has a block diagonal form in which each block corresponds to the eigenvalues of the charge q we are considering. That, for example, if it's a U1 charge, as the one we will consider in this talk, these are just numbers, okay? And in a block diagonal form, so that we can decompose the reduced density matrix as direct sum of the various blocks. Okay, and I will use this notation, which is very important. I will normalize each element by the probability PQ of finding the state in the sector of charge Q times a commutative density matrix rho of Q, which defined in this way is properly normalized to have its trace equal to 1. Okay, so we can define the symmetry resolved entanglement entropy as the von Neumann entropy connected with this rho A of Q. Okay, so for each sector here we have an entanglement entropy. Okay, and this is the topic of my talk. In particular, the symmetry resolved entanglement satisfies some rule which is written here. So the total entanglement is not equal just to the weighted sum of the various symmetry sector, but there is also this term here, which is due to fluctuation of the charge between different symmetry sectors. In the literature, this object usually are known as configurational entropy and number entropy. Number entropy because usually the charge that is considered is the number. And one of the reason why in many physical contexts these two guys behave in very different way. For example, there is this very famous paper by the group of Martin Greiner in Harvard, where they consider the time evolution of a many body localized system. Now, this is not too much important what exactly they do, but what they see is that the time evolution of this particular system, the entanglement entropy as was known, this behavior that first grows quite quickly, then it has a plateau, and then suddenly starts moving very slowly logarithmically. This was already known from before that this was the behavior, but what they show in this experiment is that the two different growth of the entanglement entropy are related to the number and to the configurational entropy. In fact, here in this plot, they show the total entanglement entropy, which is the violet curve, and you can see that the number entropy is this blue one. It's just the entire contribution to the entanglement entropy up to some time, and then only after the configurational entropy starts developing. The interpretation, actually, it's also quite interesting that, okay, before the system should have different sector of charge populated, okay, and that's why there is this rise of this growth of entanglement at short time, but then the charge gets more or less frozen, and some entanglement between each single sector start creating with time. Okay, so we see that studying these symmetries of the entanglement, one understands more what happened to the system than by studying the total entanglement that was completely transparent to this quite interesting physical mechanism. Okay, and now the symmetries of the entanglement has been studied in really a lot of work by myself, but also by many other people that are listed in these slides. And of all this work, I will consider just very small spots, trying to convince you that this is something interesting to do. So I want to start with the symmetry resolution of a U1 charge in a system which is conformal invariant, which means that is scale invariant, or we are at a phase transition, a quantum phase transition. Okay, what we want to consider is this these Rayleigh entropies of the charge Q, which are defined, as I said before, and then taking eventually the limit for n that goes to 1 to obtain the von Neumann entropy. But to compute these kinds of objects, it's clear that one should know the resolution of the spectrum of the reduced density matrix in terms of the charge Q. This is something extremely complicated to do. Then there was a very nice idea developed by Moshe Gossan and Eran Selam, where they pointed out that one can construct this sort of generating function of the Rayleigh entropy, which is a charged object in the sense that one considers trace of rho e to the m times the flux charge e to the I QA alpha, where QA is exactly the charge we want to study. And if we have this object, we can take the Fourier transform of this guy to get the symmetry resolved moments of the reduced density matrix, which means the trace of rho of to the power n restricted to the sector of charge Q, and then by simple algebra getting the Rayleigh entropy and taking the limit that then goes to 1, even the von Neumann entropy as written here. Why this? Okay, so this is already something much easier because one mapped the calculation of something extremely complicated in some local objects, which is what we like to do, and in conformal field theory for reasons that I'm not going to explain. Here they take a particular simple form as the partition function on a strange Riemann surface. Okay, for the expert, they can understand, else just don't worry too much. You don't need to know details of what I'm saying here. The important thing is that this charged entropy are equivalent to 2-point function. That's something we can calculate. And of this 2-point function, we know also the scaling dimension of the operator that enters here, so that this 2-point function is just a power law with some factor. Let's be concrete and let's consider a Ratzinger liquid, which is a prototypical system for conformal field theory in condensed matter, which is just a boson with some compactification radius, and the charge is just given by the derivative of the boson. In this case, the scaling dimension that I wrote before is just this quadratic form in alpha that is written here, so that, let's go to the interesting part, the charge moment assume this form, and in particular, they are Gaussian in alpha. Okay. Now, if we want to go to the charge moment, we should take the Fourier transform of this guy. But the Fourier transform of a Gaussian is again a Gaussian in Q. And so we have that various moments in each sector are, apart from many factors, Gaussian centered around the mean value with a width that is proportional to the logarithm of L. By then, from the probability, one can move to the entropies, and one obtained this very nice formula for the symmetries of the entropy, which tells that the first very important result, which is known as entanglement equipartition. You see that the entropy of each sector is equal at leading order to the total entropy. Then there is some correction at order log L here, okay, which is also equal for all the sectors. There is some order 1 correction, again, that is also equal to for all sector, and then there are subleading corrections that are not accessible in CFT. So what one gets, that is up to order 1 in L, the length of the subsystem, the entanglement is the same in each symmetry sector. And this is something quite remarkable, actually. One of the main curiosity that can come here is, okay, but in these symmetries of the entanglement, there is this log term, where this log term ends up in the total entropy. Okay, this is quite easy to understand, thinking to the sum rule that we wrote before in terms of configurational and number entropy. We have that if one calculated number entropy using the probability that is encoded in this probability here, Zn of Q, one gets that the number entropy as leading behavior is log L, and then there's also this factor 1/2. Okay, and this shows that this log L term is completely cancelled, exactly cancelled by the number entropy in the total entropy, and explaining what happened. And one important observation is that the number entropy is much smaller than the total entropy. Okay, which is of the same order of the symmetries of the entanglement. And this fact that we see here for a very specific case actually is valid much more in general for many other systems. And okay, which is an important finding. Okay, one can wonder, studying a specific model, for example, free fermion, can we understand that which order equipartition is broken? Okay, so that's what we asked in this paper with Riccardo Bonsignore and Paolo Giro a couple of years ago. And okay, I want to make a long story short, that also this system of, in this system of free fermion, which is a time panning model, the entanglement entropy can be analyzed by means of some technique known as Fisher-Hartwig theorems, and these charge moments can be exactly calculated in this case, and one can recognize them in this formula, the mean number of fermions that is written here, the average, which is the average of the charge we are considering, the dimension of the scaling operator that exactly agree with what predicted in terms of CFT, and we have an exact description of the order 1 term in alpha here, which is given by this nasty integral here, but that now, knowing exactly this object, by taking the Fourier transform and then taking the ratio to calculate the entropy, one can construct systematically all correction to the symmetries of the entropy. And here I just report the first ones to show that the leading terms are exactly the same as predicted by conformal field theory, showing that, okay, everything is working well. And the subleading term actually at order 1 over logarithm of L square show a breaking of equipartition. Okay, so there is this term that is Q minus average value square. So this depends on Q and breaks equipartition, and it is at order 1 over log L square. The correctness of this formula can be tested easily in numerics, as is done here, and the numerics agrees very well with the analytic results. Okay, and this one-dimensional system are actually also the starting point to study higher dimensional configuration of free fermion and boson. Okay, and even in this case, one finds equipartition, which is broken, and some subleading term. I will not enter too much in the details, because now what I would like to do in the remaining 5 minutes is to discuss what happens in non-equilibrium. Okay, and so we have in mind the non-equilibrium situation of a quantum quench in which a system is prepared in a low entangled state psi naught, and is let evolve unitarily according to some Hamiltonian. Okay, to make a long story short, again, in integrable models, the entanglement dynamics is captured by the quasi-particle picture, which was proposed long ago by myself and John Carey, and then has been refined again by myself with Vincenzo Alba. In this dynamics, what we have is that the entanglement actually is due to the propagation of pairs of quasi-particles that move ballistically through the system, okay? And so the entanglement entropy just grows linearly in time and then saturate to some extensive value. And in formula, this behavior is encoded in this very easy formula in which there is the integral over the momentum of the various quasi-particle. And okay, depending if you are inside or outside the light cone, these light cones here, you get the contribution from the linear part UVKT or just an extensive behavior that is given by L. Okay, adapting this quasi-particle picture to the charge moment, what we did was to conjecture a general form valid for an generic integrable model. But the difficult thing is that it is in general difficult for an integrable model to calculate this kernel that appear here, while this is possible for the normal entropy. But okay, we can at least compute this kernel function that we conjecture here for free fermion, as is written here, for example. In this plot here, we report the results numerical and conjecture for the time evolution of charge moments after a quench in the nil state in the free fermion models, and one obtains curves that perfectly match the conjecture, perfectly match the numerical result. Now we take the Fourier transform to go to the charge entropy, and here the most interesting things happen. That there are some very general features in the charge space here. First of all, you see that these are the entropies for various sectors, sector 0, sector 10, sector 20. You see that each sector starts with a time delay, which is proportional to the difference of the charge from the mean value, and for free fermion is calculable, okay, and it's just given by pi delta q divided by 4, and this time delay can be understood as the time needed to change the charge of an amount delta q within the subsystem A we are considering. And then after this charge delay, there is a basically linear growth of the entanglement entropy until there is a slow saturation at later time. Okay. Then there are some interesting facts. The saturated value show equipartition for small values of delta q. Okay, and again, which means that they are all the same, but there are corrections that are order 1 over L in delta q square. And another interesting fact is that the number entropy also goes like 1/2 logarithm of t. So while each entropy grows like linear in t, the number entropy grows logarithmically, at least showing that it's much smaller than the leading total entropy. Okay, and this is extremely important for many applications. Okay, but I want to conclude, my time is almost finishing, with the application of this idea to an ion trap experiment and something that goes under the name of symmetry resolved dynamical purification. This is some work that I've done in collaboration with, especially with Marcello Almonte and Vittorio Vitale at SCTP, but also with Peter Zoller, Barbara Kraus, Andrea Selbden, and others at Innsbruck. Okay, so what we want to study here is what happens when we have both Hamiltonian and dissipative dynamics as encoded in this Limbladian equation here, okay, which is exactly what describes the experiment of ion trap that is performed in Innsbruck. Now, one knows that the entropy grows under the unitary dynamics. I just reviewed it before. And we also know that even under the non-dissipative evolution, the entropy should grow. Okay? And this, in fact, is true for the total entropy. But what happened to the symmetries of the entropy? Will it also grow in any time? Okay, and if we call about purity, which is trace of rho square, it's just it has the opposite behavior, should decrease under time evolution, will always decrease, or there is some possibility that increase. It was very surprising from us to see when we were analyzing the experimental data that while the sector 0 of the entanglement entropy actually decreases as expected the purity of the sector 1 and -1, so the first one close to the the average value, actually first increase in time, so there is a dynamical purification, okay, and then decreases as it should for a long time because also of the second principle of thermodynamics. So this is really a must that at some point should start decreasing. But this initial increase of the entropy is extremely surprising. And okay, we saw it in the experimental data of the group of Innsbruck that there is this dynamical purification at intermediate time. And this dynamical purification can be understood in terms of perturbation theory in gamma, which is the strength of the dissipation into the system. And as you can see, for arbitrary value of gamma here, in this sector 1 and -1, okay, if they are not too large, there is always dynamical purification, okay, and instead, then at later time it always decreases, and there are also following other purification in the system that you can see here, but then in the end, the standard monotonic behavior of purity towards lower value always take place. Okay, I think, how much time do I have still?
Well, I think that your time is gone. So.
Okay, then I will just stop here. I will not show about the, I'm okay to stop like this. Okay, what I want to say is that the main message of this talk is that symmetry resolution of entanglement provides a fine structure of the entanglement complex of many body state, which is actually some very interesting feature. First of all, is measurable in experiment. Actually, it has been already measured. Okay, it's easy to compute theoretically, as I showed, and it has relation to many contexts that I didn't mention here, that are charge statistics, entanglement Hamiltonian, and many other things. Sorry, there is just last, this is not for this talk. Okay, and let's finish here. Thank you for your attention.
Okay, thank you for your very nice talk. I can check if there are questions on the YouTube channel. There are not at the moment. Well, more than a question, actually, I have a curiosity. Well, you mentioned this the case of quantum quench.
Yes.
Okay, you have very nice analytical formulas. And my question is, I do work on quantum annealing. Are there some prescriptions on the time scale over which you can apply your formalisms? How fast has to be the quench in order to
Yes, okay, clearly the quench.
Yeah. In this case, yeah.
The quench has to be faster than the many body gap. Else you see the discreteness of the spectrum, and okay, you are.
So you are way in the opposite limit of the quantum annealing.
Exactly. It's just
okay. Okay. Let me see if there are. Okay, there are no other questions. So in this case, I thank the speaker again. Grazie, and I would move to the next speaker of today's session.
Okay, I will stop screen sharing.
Yes, please. So the next speaker is Davide Girolami, that will give a talk on quantifying the difference between many body quantum states. Well, okay, so you have 20 minutes plus 5 for discussion.
Okay, hi everyone. Thanks a lot for the opportunity of speaking today in this conference and for bringing back this conference. Today in this talk, I want to tell you about an important problem related to many-body quantum systems. I will show how to draw meaningful comparisons between their complex configurations by introducing a new concept in quantum information theory, the concept of weighted distances. This discussion will be instrumental to derive my main result, that I will state here, It's a fundamental limit to quantum information processing. Our ability to process quantum information in a precise technical sense I will define later is never greater than the related experimental cost. For all the technical details, the proofs and so on about this talk, you can look at these two papers, in particular to the most recent one, which I wrote in collaboration with Fabio Anzà. So let's start our discussion. The scenario I want to tell you about today is the following. You have a system, say, of n qubits, but the dimensionality of the components is not important. Say you prepare two different states of such a system, the blue state and the green state. Question, how can we quantify the difference between these two states? So this question is kind of vague. We can attack this problem from many different viewpoints. Here I want to discuss two main ways to answer this question, and then I want to show that they are kind of surprisingly related. The first way to answer the question is to define the difference between two quantum states as the ability to distinguish them by making measurements. Here is what you can find in the literature. Suppose you have a system, you prepare two copies of this system, the blue configuration and the green one. Suppose you have two pure states, so the blue configuration is psi n and the green configuration is phi n. Then you make a general measurement, a POVM on these two states, the same one. You collect measurement results, you build probability distributions for these measurement results, and then you measure how different are these probability distributions. Well, it's possible to prove that the difference between these two probability distributions, in the case of the best informative measurement, is given by the Fubini study distance that I here define. That's great because the Fubini study distance is related to the state overlap, which is the textbook way to quantify the difference between two wave functions. So the Fubini study distance is 0 if and only if the two states are the same, and is maximal is equal to 1 if and only if these two wave functions are orthogonal. This is well known. It's great because you can see that the quantification of the difference between two states in terms of ability to distinguish them, let's call it a metrological way of quantifying the difference between two states, as a nice geometric interpretation as a distance in the abstract space of wave functions. You can generalize this argument to density matrices. This is well known too. Now you have rho n and sigma n, two generic density matrices that represent mixed states of our system. We make a POVM, and in the best case scenario, we can build the state fidelity and then a distance function. There are several options, but for this talk, I will pick the Beer's length. That is also formally related to the Fubini study distance. Okay, now the fidelity, the related distance functions are ubiquitous in quantum information science. They appear in basically every theory paper. Also, experimentalists love evaluating the performance of their work by calculating the state fidelity, for example, between the state that they obtain in the laboratory and the desired target state. However, these quantities, despite their popularities, suffer from some pathology. I want to explain what I'm talking about with two examples. Consider this following scenario. The blue state is just a boring sequence of 0, while the green state is a state with one excitation. So I flipped one qubit. Well, these two states are orthogonal. The overlap is 0, and they are maximally distant, far in terms of Fubini study distance. And this is true for any value of n. However, for large n, these two states are very, very similar. It should be very, very difficult to distinguish them by making measurements. Second problem. Suppose again the blue state is a boring sequence of 0, while the green state is a state that displays n-particle entanglement, long-range entanglement. The overlap between these two states is again independent of n. in particular is equal to the absolute value of this coefficient A. Now, the distance again doesn't scale, the Fubini study distance doesn't scale with n, the Fubini study distance between these two states. That's bad because these two states are very different from each other for large n, we know that. Also, for very large values of A, say A equals 0.9999, the overlap is very big, so the Fubini study distance between these two states is very small, but these two states are still very different because the green state still displays long-range entanglement. Okay, so how can we get rid of these paradoxes? We build a new class of metrics, the weighted distances, that does not display these pathologies. How can we do that? So this is the most intricate slide of the talk, so bear with me, please. We can do the following things. Here is an outline. You can find all the technical details in the paper. So you construct two copies of your system in the states rho n and sigma n. Then, second step, you divide your system in clusters of size k1, k2, and so on. So the sum of all the case is equal to n, the number of particles. So this partition can be called pk alpha, okay? Of course, you can have many different partitions. Then, for every cluster, you compute the Beer's length, the standard Beer's length, B rho k1 sigma k1, B rho k2 sigma k2, and so on. Okay, the argument is valid for any standard distance you want. Here I use the Beer's length. Other step, you build a weighted sum of these distances, of these Beer's Beer's lengths related to each cluster. So the weighted sum that I call delta B pk alpha is defined in this way. It's the sum over all the clusters of 1 over k alpha times the Beer's length that quantify the difference between the marginal density matrices of each cluster. So the weights, let's study now 1 second the weights. The weights are the inverse of the size of each cluster. So there is a weight 1 over k1 for the cluster of k1 subsystems of k1 particles, 1 over k2 for the cluster that contains k2 particles, and so on. That is, in this weighted sum, every contribution is weighted in terms of how easy it is actually to compute this Beer's length. Why? Because if you assume that the larger is the subsystem, the more difficult experimental is to carry out the measurement to being able to compute this Beer's length, then the inverse of the size of the cluster, the inverse of the size of subsystems that consist of the clusters, is a measure of how easy it is actually to compute this B rho k alpha sigma k alpha. Okay, so we build this weighted sum. Finally, last step, we maximize this weighted sum over all the possible partitions pk alpha that we can think about. Okay, this quantity, this dB rho n sigma n, is the weighted Beer's length. Okay, so we have proven that this quantity satisfies a set of desirable mathematical properties, and also we computed in some particular cases we derived analytical expressions of this quantity. Here I want to show you some examples. In the paper you can find more of them. So in the left column of this table you have couples, pair of states to be compared. In the central column you have the Beer's length, the standard Beer's length. In the right column you have the weighted Beer's length, okay, the new quantity. So in the second row you have the first example. You have a sequence of 0 compared with a state with k excitation. So the Beer's length in this case is constant. It does not depend on k. That is bad. While the weighted Beer's length is proportional to k. So it quantifies exactly what we want. Second example, you have a boring sequence of 0, and then you have a GHZ state, so a state that displays m-particle entanglement. Again, the Beer's length is constant between these two states, while the weighted Beer's length is proportional to n. And this makes sense because the larger is n, the more different these two states are. Finally, last comparison I want to talk about today is the one between the GHZ state and a state that displays only classical correlations. So this example is significant because these two states, class n and GHZN, are the same if we just trace away one qubit. Okay, so we can distinguish them only by making a measurement of over all the n particles. Okay, the Beer's length, again, is constant, while the weighted Beer's length scales like 1 over n. So this makes sense because the larger is n, the more difficult it is to distinguish between these two states. Therefore, these two states has to be closer and closer metrologically. Great. This is the first way to quantify the difference between two states. Now let's consider a completely apparently unrelated way, a computational way. Suppose you have your system again of n qubits, you prepare it in a mixed state rho n, and you want to transform it in a state sigma n. We can quantify the difference between these two states in terms of the size of the best algorithm that send your system from rho n to sigma n. Here, obviously, I'm considering two states, rho n and sigma n, that have the same spectrum, but the argument can be generalized. Okay, let's assume they have the same spectrum for this talk. This problem has captured the attention of some influential guys, Nielsen, Aronson, Susskind, and so on, that studied this problem actually for pure states only. Also, they pick as a cost function to be minimized the size of the algorithms. It asks the number of gates that make the algorithm to transform the initial state to the input one, to the output one. Excuse me. So what I did, I generalized the studies to mixed states, and I also pick more nuanced metrics to be minimized. In this way, I found a measure of the computational difference between two arbitrary density matrices, and I discovered, together with Fabio, that state discrimination in metrological way and this computational way to quantify the difference between two states are related. And this was kind of surprising because in literature, they've always been considered quite different tasks. Here I'm quoting some words of Munters, that is one of the pioneers of this subfield. Let's see how it's possible. So consider a general unitary U, okay? And you define it in terms of a time-independent Hamiltonian H and the time t. This unitary acts on k qubits. Then you define an energy parameter E in terms of the difference between the maximal and minimal eigenvalue of the Hamiltonian H divided by 2. Okay, there are several theoretical motivations for using this parameter, okay, that are all discussed in the paper. Now, we can quantify the required experimental resources to implement a general unitary U in the laboratory by this new coefficient RU, by this resource counter RU. This coefficient is defined as follows. It's the product of the system size, so the number of qubits that are involved in the experiment, K in this case, times E, the energy parameter, times the time T. Okay, now I'm thinking about algorithms, so I'm thinking about a sequence of unitaries. So if I define the unitary U as a product of unitaries UL, well, the resource count of RU is just the sum of the resources that are needed to implement each UL, okay? Well, we've been able to prove that to complete a transformation from rho n to sigma n by implementing this unitary U, the resources, the physical resources as quantified by RU, are never smaller than the weighted Beer's length between the input and the output state. So what does it mean then? It means that our metrological ability to distinguish between the input and the output states is never greater than the experimental cost to complete this transformation in the laboratory. In other words, these two different concepts of difference between two quantum states are strictly related. Okay, let me recap the situation. I discussed two different ways to quantify the difference between quantum states of many-body systems. The first one is a metrological one, and it represents the difference between quantum states in terms of our ability to distinguish them by making measurements. In the field, despite their popularity, fidelity, and related distance functions are of course useful, but suffer some pathologies. So what we did, we constructed weighted distances, so new alternative metrics that doesn't suffer this pathologies, and therefore they can be useful quantities for this task. Then we consider a different way of calculating the difference between the quantum states, a computational way, to what a more physical way, in terms of the size of the algorithm linking two states. And we found that these two different approaches are kind of surprisingly related, and this relation can be formalized in this simple inequality. The states basically that our ability to transform a given input state in a state that is metrologically distinguishable, in this sense, to process quantum information, is upper bounded inevitably, but by the experimental resources that are needed to complete this experiment. Thanks a lot for the attention.
Thank you very much, Davide. I just have a question. I mean, as an experimentalist, so it's maybe it's completely silly for you, but just I was thinking that the distance that you define is unbounded, while the distance based on fidelity is strictly bounded by 1. Has this feature some physical meaning, or is it just a mathematical problem?
Well, as you can see also from this bound, this weighted distance is more related to actually the experimental resources that you need in the lab, right? Because for transforming a sequence of n zeros to a sequence of, so for example, GHZ state, n matters, of course, right? It's more difficult if n is equal 1 million than if n is equal 2 or 3, right? So this weighted distance actually capture this thing, while the standard distances, because of their normalization, don't capture that.
Okay, thank you very much. So I just check if there are questions on YouTube. No, there are no questions so far, so we move on. Thank you again for your very nice talk. And we move to Gustavo Martin Bosic, that will talk about generalized coherence vector definition and application.
Okay, thank you.
Hi.
Hi. I will share my screen.
Yes.
Okay. Can you see?
Yes, we see your screen, and now we see your presentation.
Okay, I will put in full screen mode.
Yes, please.
Okay. Well,
you have 20 minutes and then 5 for discussion. Thank you.
Okay, perfect. Well, first of all, thanks to all the organizers for allowing me to present my work. I hope the next time to present my work in person. Okay, my talk is about our work about the introduction of the notion of generalized coherent vector and some applications in the problem of state transformation and the definition of coherent measures. I divide the talk in 2 parts. In the first one, I will briefly introduce the resource theory of quantum coherence, and in the second one, I will present our results. Well, as you know, every quantum resource theory is based on 3 basic concepts: the free states, the resources, and the free operations. And with this notion, we can construct any quantum resource theory. For instance, the typical example of a quantum resource theory is the entanglement theory, where the free states are the separate ones, the resources are the entanglement state, and the free operations are the so-called LOCC operations. So this framework we can use not only for entanglement, we can use this framework of the formalism of resource theories for another property of the quantum system. For instance, to address the problem of quantifying the superposition principle. So the notion of quantum coherence is about the superposition principle with fixed orthonormal basis. The orthonormal basis could be, in principle, the initial state of any observable of interest. Here, we choose the coherent basis as the computational basis because we can do this without loss of generality. So once the coherent basis is fixed, the notion of coherent state is just any diagonal state in this basis, okay? And other non-diagonal state in that basis is coherent. This is the definition of free states and the resources of the theory. Well, regarding the free operations, they are for coherence, there are a lot of proposals. Here, we will follow the proposal given in this paper of 2014. So the idea is that we have any quantum map. We know it's a complete positive 3% map, and they emit a Krauss representation. So the idea of any coherent operation is that a quantum map has to map any quantum state, any incoherent state into incoherent state. This is the set of maximally incoherent operations. If we restrict this set, saying that, okay, we map incoherent even in probabilistic way, we are defining the incoherent operation. Formally, an incoherent operation is a quantum map that admits a Krauss representation that each Krauss operator map incoherent state into incoherent state. Okay, so we have the three ingredients of the theory: the incoherent state, coherent state, and the incoherent operations. So there are two common problems in any quantum resource theory. One problem is the characterization of the state transformation. So we aim to answer this question: given rho and sigma, is possible to transform rho into sigma by means of the free operation of the theory? This is one typical problem. And another one is quantifying the amount of resources. So given rho, in quantum state rho, we want to know how many resources the state have. We want to have a number. So we address these two problems within the resource theory of quantum coherence. I now introduce two important notions that allow us to answer this question. The first one is the notion of coherent vector of a pure state. Given the incoherent basis, the coherent vector of a pure state psi is just defined in this way, where, for instance, the A component is just the square modulus of the inner product between the state psi and the A element of the incoherent basis. Okay, it's clear that this coherent vector is a probability vector because all its components are positive or equal to 0, and the sum of all of them is equal to 1. So this is the definition of probability vector. We call PD the set of all the dimensional probability vector. The other notion, which will be very useful in the resource theory of coherence, is the notion of majorization, which is a previous notion. It's mathematical, no? Because majorization allows us to compare, in general, vectors, but in particular, probability vector in this way. Given two probability vectors U and B, we say that U is majorized by B, and we denote with this symbol if and only if all the partial sum of the first vector is lower or equal to all the partial sum of the other vector. We have to pay attention here in the down arrows. That means that the vectors U and B, its components are sorted in decreasing order. So in order to compare, we first sort the component of U and B in decreasing order, and then we compare each partial sum. So if all these inequalities are satisfied, so we say that U is majorized by B. Which is important that this notion of majorization from the order theoretical viewpoint is a pre-order, which means that satisfy the reflexivity property, U is always lower or equal. U is always majorized by U, and it's transitive. So if we have U is majorized by V and V is majorized by W, this implies that U is majorized by W. Okay, but majorization is more than a preorder. If we consider the set of all probability vectors PD, where the components are sorted in decreasing order, we call PD than auror. Well, we have also the antisymmetric property. So we have a poset, a partial order set, and moreover, we proved in 2019, and there are other works that prove the same, the infimum and the supremum of any subset exist. Okay, this will be very important for us to generalize the notion of coherent vector from pure to mixed state. And in this paper, we provide an algorithm to compute the supremum for any subset. Well, regarding these questions, given rho and sigma, it's possible to transform rho into sigma by means of the free operations. Well, there are two important results in the literature. The first one, solve the problem completely from the case pure to pure. If we have a pure state, well, the pure state psi can be transformed in the final pure state phi by a means of incoherent operation if and only if the coherent vector of the initial one is majorized by the coherent vector of the other one. This is proved in this paper in 2015. Moreover, one pure state psi can be transformed into now a mixed state sigma by means of incoherent operation if and only if there exists an ensemble such that this ensemble of pure states first generates the state sigma. So this is a pure state decomposition of sigma. This is the first condition. And the second one, the coherent vector associated to this state is majorized by this probability vector, where we can see here that this probability vector, this sum, is a sum of probability vector weighted with this probability. Okay, and this is the coherent vector of the pure state of the sample, well, order where the components are ordered in decreasing order. So in the case of pure to mixed state, we have two conditions. Well, the another question is, given rho, how much coherence the state is have, okay? Well, the axiomatic characterization of this question is given by the introduction of the definition of coherent measure. So we say that a coherent measure is a function from the set of quantum state to the real, satisfying the following conditions. Well, these are minimal conditions that any coherent measure has to satisfy, are very natural to say that, for instance, the coherent measure C has to vanish for incoherent state. We assign the zero value to incoherent state. If the coherent measure has to satisfy the monotonicity condition, which means that the coherence decrease under the action of incoherent operations. Okay. Moreover, a coherent measure has to satisfy the strong monotonicity. That means that the coherent decrease not only decrease in average and the action of incoherent operation. This is the third one. The fourth one is we assign the maximum value of the coherent measure is attained if only if the state is a maximally coherent state. And the last one is the convexity. So the coherent measure of any convex combination is lower or equal than the convex combination of the coherent measures. Okay, so we say that any measure C that from the quantum state to the real that satisfies this phi condition is a coherent measure. If we relax the last one, we say that the function C is a monotone, it's a coherent monotone. Well, in order to define coherent measure, it's important to introduce this set of functions. The set formed by all symmetric and concave functions with these two additional conditions, which means that the function evaluated in this vector, in the 1 and 0s, is 0, and the function obtains its maximum value in the uniform probability vector, 1 over the dimension. This function will be important in order to introduce the coherent measures and are related to the notion of majorization, because this is a result of the literature that any symmetric and concave function is a sure concave function, which means that anti-preserve the majorization relation. Well, how these functions are connected to the notion of coherent measure? Because given a coherent measure C, there exists a function f in this set such that the restriction of the coherent measure to the set of pure state, denoted in this way, is just the function f applied to the coherent vector of the state, the pure state. So we have here the notion of coherent vector and the notion of symmetric and concave function. With this, all coherent measures restricted to pure state can be written in this way, as a symmetric and concave function applied to the coherent vector of the pure state. Well, the aim is to start with a coherent measure defined from pure state is to generalize to the case of mixed state. And in the literature, there are two ways to do this. Okay, this is the problem. Given a function f, we can define a coherent measure from mixed state in the following way. Well, the first method is based on the common roof method. So we have this plot, which means that we have the set of convex, the set of all quantum states. We know it's a convex set, and we know that there are many pure state decomposition of the state row. This is one, this is other one. So we call the set of all pure state decomposition row the row. Okay. So the convex roof measure of coherence is defined in this way. You assign for each pure state decomposition, you evaluate the function f associated to the coherent vector of the k element of the pure state decomposition, and then sum over all the pure states. And taking this is for one pure state decomposition. Then taking the infimum among all pure state decomposition of the row, you have this definition, which is the convex roof measure of coherence. And it's proved in these two papers that this measure satisfies the previous conditions, the 5. So it's a proper measure of coherence, and is the among all coherent measures is the biggest one. Okay. There another proposal more recently, which is based in this observation. Given rho, there are many pure state that can transform it into row by means of a free operation. So we can define this set of the row, which are the set of all pure state that can be transformed into row by means of incoherent operation. Okay, this set is not empty because obviously the maximally coherent state belong to this set. So how to define a monotone? Starting with this observation, okay, you assign to each pure state, we define the coherent vector of this pure state, and then we apply this function f. Okay, at the end we take the infimum amount of all pure states that can be transformed into row. Well, it was proved that a function defined in this way satisfies the 4 previous conditions. In general, this function is not a convex, it's not a convex function. And this definition also satisfies this property. For any function C that satisfies the previous 4 condition, well, this one is the biggest one. So here we have a summary of the result of the literature. So the message here is the notion of coherent vector of pure state is important, not only to characterize the pure to pure and pure to mixed transformation, also to introduce in 2 different ways coherent or measure coherent monotones. Okay, so our aim is to extend this notion, the notion of coherent vector, from pure to mixed state, and then apply it to this problem, the problem of state transformation and the problem of defining new family of coherent measures. So we have 2 proposals to extend the notion of coherent vector from pure to mixed state. The first one is motivated by the convex rule of this observation that the set of quantum state is a convex set and we have infinite pure state decomposition. So suppose we have this particular pure state decomposition of row. Well, we can define this probability vector is in this way. This is the coherent vector of the K element of the pure state of this ensemble weighted with this probability, and we can sum over all the state of the ensemble. Okay, this is the probability vector. It's like the probability vector of the ensemble. Sorry, the coherent vector of the associated to this particular ensemble. Well, now we take all probability vector associated to all the ensemble of row. Okay, and we have this. This is a set of probability vectors, and we know this is a set of probability vectors. It's a subset of the probability vector of the marginalization lattice. So we know that this set has a supremum because the marginalization lattice is complete. So we can define the coherent vector associated to row as the supremum in a set of marginalization of this set. Well, a trivial observation, if we evaluate this definition for a pure state, we recover the notion of the coherent vector of the pure state with the only observation now is the coherent vector are its components are sorted in decreasing order because all the probability vectors are sorted, its components are sorted in decreasing order. So this is the first proposal. The second one is inspired in the top monotone, no? Because we have row and they are infinite, infinite. There are many pure states that can be transformed into row by means of incoherent operation. And to each one of these states, we can assign its corresponding coherent vector. sorted in decreasing order, and we define this set, the set of all period, the set of all coherent vectors associated to the period state that can be transformed into rho. Okay. Again, this is a subset of the majorization lattice. So this set has a supremum in the sense of majorization. So we can define another principal coherent vector rho in this way as the supremum of this set. Again, this is an extension of the definition for period state, because if we evaluate this definition to the case of pure state, we'll recover the definition of coherent vector of pure state. So now we prove that these two definitions coincide, okay? Because we have two observations. The first one is the set formed for the probability vector from the pure state composition rho is a subset of the other probability vector formed from the set of the pure state that can be transformed into rho. This is this condition, and because this is true, this implies that the supremum on this one is majorized by the supremum of the other one. In addition, we prove that for any vector u in this set, there exists another one here, such that this one, the u prime, majorizes the vector here. And this condition implies that the converse of this inequality, of this majorization relation. So we have on the one hand we have this relation between the supremum. On the other hand, we have the inverse relation. So because the majorization lattice satisfies the antisymmetry property, these two conditions implies that both supremum are the same. So we have only one definition of generalized coherent vector. So we say that the coherent vector of rho is the supremum of this set or the supremum of the other one. Okay, both definitions coincide. And moreover, okay, we have now a definition. Okay, two proposals give us the same result, but now we want to ask if this definition is a good definition or not, if characterizes some properties of the coherence of rho. Well, the answer is yes, because this definition satisfies these 5 properties. The first one says that if we have an incoherent state, if and only if the coherent vector of the state is the 1 and zeros, okay, the secondary probability vector. Also, this definition characterizes the notion of maximally coherent state. Rho is a maximally coherent state if and only if its coherent vector is the uniform probability vector. In addition, satisfy the monotonicity property in this way. The coherent vector of rho is majorized by the coherent vector of the transformer state, where the transformation is given by any coherent operation. Moreover, satisfy the strong monotonicity in the same way before, that here, instead of have this, we have the convex combination of the state after the transformation. And the last one is we only prove that this definition is concave only for the case of pure state composition. We cannot prove this property instead of putting here pure state, mixed state. So we have a conjecture here, but at least we have this property. So this is a good notion of generalized coherent vector because it's well motivated, because it's motivated by the convex roof and the top monotone, and also because we have these 5 properties. Okay. Now we can return to the first question. Well, in the more general case, we want to answer if given rho and sigma, general state, not pure or mixed, general and general, well, it's possible to transform rho into sigma. Well,
you have only 3 minutes left.
Okay, well, I finish. I will. Well, we have because the monotonicity, we have a necessary condition for the state transformation. Okay, we can say that rho can be transformed into sigma. This implies that the coherent vector of rho is majorized by the coherent vector of sigma. Well, in particular, if both coherent vectors are incomparable, we don't have a majorization relation between them. This means that the quantum states are not converted by means of incoherent operation. Okay, we can put this in this Hasse diagram, and we have the counter-reciprocal of this. If we have the coherent vector of rho is majorized by the coherent vector of sigma, and both coherent vectors are not the same, this implies that sigma cannot be transformed into rho. So we have this situation. We have the coherent vector of sigma is majorized the coherent vector rho. Well, this transformation is not allowed. Okay, but we can say nothing about the opposite. Okay, if this is below to this in the state of majorization, this does not imply that rho can be transformed into sigma. For that reason, we can answer we have solved only a necessary condition. Well, to finish, regarding to the second question, given rho, how much coherence the state has? Okay. Well, we can define a new family of coherent monotones just in this way. The coherent vector monotone of rho is just a function f evaluated in the coherent vector of rho. And this definition satisfies the 4 properties of being monotone, while in general it's not convex. This plot is a comparison of the 3 proposals of the coherent monotone. We have the top is always greater than our proposal and the convex roof, and between our proposal and the convex roof, there is an order relation. Our could be greater, equal, or lower than the convex roof, and we have several examples showing this. Just 2 examples. Given a qubit with coherent vector R, Rx, Ry, Rz, well, we show this closed formula for the coherent vector in terms of the block vectors. Okay, and in this case, the 3 proposals are the same for any function f. So in order to see a difference between these families, okay, we have to go to a higher dimensional system. For instance, consider a maximal Q3 state going through a depolarization channel. So we have a common combination of the identity matrix over 3 and this maximally Q3 state, and fix this function, which is a particular function in this set. And we evaluate the 3 families for the function, the 3 monotones for the function, in terms of the probability of the polarity channel P. In this case, in the blue curve is corresponding to the convex roof, which in this case is equal to the top monotone. And the orange is our proposal, our measure. So it's clear that in the extreme cases, P equal to 1, the maximally here, sorry, p equal to 1 is the coherent 0 because we have a coherent state, and in p equal to 0 we have the maximum value because we have the maximal coherent state. In the middle, okay, the converse roof or the top monotone is greater than the coherent vector. So to finalize, okay, we provide the suitable definition of coherent vector for the general case. We partially answer this question of the state transformation. We provide necessary condition, and also we define a new family of coherent monotone based of the notion of coherent vector. Well, thanks to all. You can find the details of this work in this paper, which is a collaboration with the Italian group of the University of Cagliari and other colleagues from Argentina. So, that's all.
Thank you very much for your talk. So with this talk, we arrive at the end of the conference. And let me check if there is any question on the YouTube channel. No, at the moment, we have no question. So please, could you switch off the sharing of your screen? Okay, so now we just are at the conclusion. So the greetings and the thanks to the participant, to all the staff that worked on this event. Filippo, Domenico, and Davide are here. Vincenzo is here. Procolo, unfortunately, cannot be here. So they have done a very big effort in helping us to organize and carry on the conference. Francesco, want to say something?
I just want to thank all of you. All people participating and the whole team. It's been a wonderful adventure since the very beginning. And I'm sure that Alberto, Saro, and Giampiero, our big thinking goes to our younger collaborators, Domenico, Davide, Procolo, Vincenzo, and Filippo. And also a big thank to our service for transmitting the whole event. They've been with us in presence and from far, and Claudio Esposito's team and Giovanni Barone, thanks so much. Without you, it would have been impossible. It's been really a wonderful adventure. And Alberto, I can't see you. I mean, I can see only David. No, and not even Filippo. Can you see that? Okay, now also Filippo. Now I see the two of you. And so really thanks to all of you. And so from my point of view, see you in Palermo next year.
Right, you're right. Here. Next edition will be in Palermo, so we wait from the colleagues in Palermo all the information for the conference.
I also would feel like saying, for us, it's been a real privilege to have the community here in Napoli, in presence and in fact. I really would like to stress that there's been a wonderful get-together. It would have been wonderful also without COVID, but with COVID it's been even better after COVID. And really a big emotion for everybody. So thanks so much to everybody. Thank you, Alberto, Davide, Filippo, Domenico, Davide, who are also here, and Giampiero. Also, you are, probably you are connected, but you are traveling. So anyway, so bye bye, and
see you next time.
See you in Palermo.
See you in Palermo. Bye bye. Thank you.
Bye. Bye bye.